Hello everyone, I'm humanHardDrive, and today on Electronics 201 we're going to be talking about Karnaugh mapping. Karnaugh mapping. So what is Karnaugh mapping? Karnaugh mapping is a means by which to simplify Boolean algebra. Simply put, you can take a logic table that you don't know a circuit diagram for and be able to take it and produce a circuit diagram for it. Now, Karnaugh mapping only does this in sets of and OR gates. So it doesn't let you combine it with, say, XOR gates, but if you know some Boolean reductions, you can take and OR gates and reduce down into X and OR gates. We're not going to be talking about that today. We're just going to be talking about the basics of Karnaugh mapping. So with that, let's get started. Let's start with something basic, a logic gate we all know. So let's say we've got two inputs, an A input, a B input, and then this logic gate, which we all should be able to recognize as an OR gate. And then that generates an output. And we should all know the logic table, or the truth table, for an OR gate. And we should all know how to draw a logic table. And there we go. So there's our mysterious unknown truth table, but we do know it, so just it's unknown. Pretend you don't know what it is. Now, what a Karnaugh map is it's sort of like a multiplication table. So you're going to draw yourself a square. This is a terribly drawn square. I apologize for that. And the order in which you draw this does matter. And I could probably do to move this a bit. There we go. And each side is an input. So this is side A and this is side B. Now the order, it has to go 0, 1, 0, 1. Okay. So, and then you just start filling it in. So A, where we say A is 0 and B is 0, the output is 0. Where A is 0 and B is 1, the output is 1. Where A is 0 and B is 1, the output is 1. And when they're both 1, it's 1. Great. Now, what you're going to do in order to reduce this, in order to take this and turn it into a logic diagram, is look for areas of sequential ones. Spaces where there are adjacent ones, like here. And if I choose another pen color, here. There we go. Now, they are allowed to overlap, and these have to be done by powers of 2. So you can have one on its own. It's not encouraged. You should try and find a place where you can connect more than one. But if you're stuck, you can use one. But you've got to find at least 2 in powers of 2. So that's 2, 4, 8, 16, 32, etc., depending on how big your map is. Okay. So we have to examine within those boxes, the red box and the blue box, or the red box and the black box, what changes and what stays the same. So in terms of the red box, B stays, A changes. Sorry about that. A changes. And in terms of, if I go back to my black marker, in terms of this box, the black box, A stays, B change. There we go. Now, in order to combine the two boxes, the result of the two boxes, you say A, this is from the black box. I don't have another color, so I'll just put OR. Plus denotes OR. A or B. And that's what results in this truth table. And as it turns out, yes, that is the OR gate we chose. Hey, we figured it out. So that's a 2x2 Karnaugh map. Now, let's move on to a 2x4. We're going to add one more input, and this time we're just going to create some generic output. We're not going to actually have a logic gate to base our math off of. So let's look at make sure I'm going back to the right color, 2x4 map. Okay, so we've got A, B, C, and the output. We just start filling in this table. Okay, so here's our 2x4 truth table with 3 inputs and 1 output. So I've just gone ahead and filled it in, used some random output data. And let's go ahead and draw our map. Now, with the previous map, the 2x2, each side was its own input. Now we've got a third input, we're going to have to combine 2 of the sides. So one side is going to be longer than the rest. So this will become the A, B side, and this will be just the C side. And pay attention to the order, okay? 0 and A and B are both false. Okay. A is false, B is true. A is true, B is true. A is true, B is false. That order matters, because otherwise the Karnaugh map doesn't work. It's all about each one has to change, and then they have to be combined. See, one changes, the other changes, and the other changes. So each one has to change in a sequential step. Okay. So, and if we go ahead and fill in this table by examining the truth table, and there we go. So I'm sure you've already seen these two connected together, so we can just draw our circle around that. But as I mentioned earlier, there may come a point where you can't draw more than 2 adjacent, or at least 2 adjacent ones together. So this one has to sit all by itself. And we'll talk about that case now. So for that, we've got to examine what stays the same and what changes. Now, because there's only one, everything is staying the same. Okay, because it's not moving vertically or horizontally, so there's going to be no logic changes. Now, we also have to take care of inversions. In order for this to work, all the inputs have to be true to make the output true. So, in this case, A, B, and C are all staying the same. Oops. A, B, and C are all staying the same. So, A is false, so that has to be inverted. Now, to join inputs on the same box, you're going to use AND, which has the multiplication symbol. B, which is already true, so we don't have to invert it. And then C, which is false, so we also have to invert that. Okay, so that's one of the inputs. That's one of the outputs. Okay. Now remember, to join boxes, we use AND. Or not AND, OR. Sorry, we use OR. OR. Examine what changes and what stays the same. Both A and B stays the same, but C changes. So we're going to ignore C. A is true, but B is false, so B needs to be inverted. And that's it for this Karnaugh map. So we've taken this truth table and generated this circuit diagram, or this logic diagram, which can be converted into a circuit diagram if you just swap everything out for the gates. Alright, now let's just talk about one more Karnaugh map, a 4x4, which is the biggest Karnaugh map we're going to talk about today. Make sure I'm on the same color. A 4x4 map. So this time we've got A, B, C, and now D, and then the output. Okay, so here's our truth table. It's a 4x4, so that means 16 possibilities for the input and just some generic output I thought of. Alright, so let's go ahead and draw our 4x4 Karnaugh map. Remember, like last time, we had to combine 2 of the sides. Now we're going to have to, again, combine another 2 sides. So this now becomes a very large Karnaugh map. So this will be the A, B side, and this will be the C, D side. Remember, the order matters, people. 0, 0, 1, 1, 1, 1, 0. And then we just go ahead and fill in the table. Okay, so there's our Karnaugh map, and now let's go ahead and highlight some of the sequential ones. So here's one, and there's one more we can highlight. Now the goal is to group them in as large groups as possible, so what we can actually do is take this entire square and group it all together. Now it has to be grouped into an entire square. Okay, because it's, again, powers of 2, and that's only going to result in squares. You can't have, well, actually you can't have, but you can, it's got to be grouped into, remember, powers of 2, and this is a 2 by 2 square. Okay, so let's start with that one first, because that'll be the most complicated. Now, again, examining what changes and what stays the same. So in this case, A stays the same, B changes, so we ignore B, and here, D changes, but C stays the same. Now C has to be inverted, but A can stay. So that's A and not C. And then we just have to combine that with the other box. Plus. Or. And then this one down here. A and B stay the same, but they both have to be inverted, so this is not A and not B, and D changes, but C stays the same, but C is already true, so we can just leave it as C. And there we go. So that is the resulting logic diagram for this logic table. Now that's really it for drawing Karnaugh maps and solving the equations. There is one other thing to talk about, and it's kind of important. I'm actually just going to try and copy this whole thing without. There we go. That didn't work. Let's try this one more time. There we are. Boop. And I'll just copy this. Move it on to the next page. And here we go. Okay. There is an interesting case. It's called the doesn't care case. And how it works is I can take, say, one of these zeros and replace it with an X. I'm sure you've seen this if you've looked at logic diagrams or logic schematics. You've seen this X. That's the doesn't care X. And what that does is it replaces any spot in the output, in this case 0, 1, 0, 1, so right here, with an X. And what you can do is you can use that to connect adjacent 1s. So if you have a 1 next to an X, the X can be treated as a 1. But you don't always have to treat it as a 1. If it's like here, it's just sitting in the middle of all these zeros, you can just leave it alone and it doesn't change the output you get. So that is it for Karnaugh mapping, including the doesn't care square. So I'm humanHardDrive. Thanks for watching.